What specific problem does the UniDisc method aim to solve in the context of multimodal generative models?
The UniDisc method aims to address the inefficiencies and limitations of existing multimodal generative models, particularly those based on autoregressive AR architectures. Specifically, it seeks to unify the generation of text and images through a discrete diffusion approach, which allows for more efficient training and inference compared to AR models that struggle with high-dimensional data. UniDisc employs a unique mechanism of corrupting data with discrete noise by randomly masking tokens, enabling it to effectively learn to map masked tokens to clean tokens across modalities. This approach not only enhances the model's ability to perform joint image-text inpainting, something previous models could not achieve without fine-tuning, but also improves inference efficiency and quality of generation. Ultimately, UniDisc aims to provide a more coherent and effective framework for multimodal generation, leveraging a unified architecture that can handle both text and images simultaneously.
Can you explain how the proposed UniDisc method works? Please illustrate it step by step, focusing on the discrete diffusion process and how it is used for both text and image modalities.
The proposed UniDisc method operates through a unified discrete diffusion process that effectively handles both text and image modalities. First, it corrupts data by randomly masking tokens, which allows the model to learn to map these masked tokens back to their original multimodal representations during inference. The forward diffusion process uses an absorbing transition matrix, where the probability of a token remaining unchanged is denoted by alpha, while the probability of it being masked is 1 alpha. During training, a bidirectional decoder-only transformer is employed, utilizing 2D rope embeddings for image tokens and 1D rope embeddings for text tokens, enabling the model to learn from both modalities simultaneously. Finally, during inference, the model applies classifier-free guidance to balance quality and diversity in generation, allowing it to generate coherent outputs across text and images effectively.
Could you provide a simple example that illustrates the inner workings of UniDisc, particularly how masked tokens are handled during the denoising process?
UniDisc employs a discrete diffusion process where masked tokens are integral to its denoising mechanism. For instance, during the forward diffusion process, a token from the input sequence can be randomly masked with a probability of 1 alpha, where alpha is the probability of the token remaining unchanged. When denoising, UniDisc learns to map these masked tokens back to their original values by sampling from a joint vocabulary of text and image tokens. Specifically, the model uses an absorbing transition matrix that allows masked tokens to remain masked during the forward process, while ensuring that they can be unmasked during the reverse process. This approach enables UniDisc to effectively reconstruct the original data from the masked input, showcasing its capability for joint image text generation and inpainting without requiring fine-tuning.
What are the theoretical or practical advantages that UniDisc offers over traditional autoregressive models, especially regarding inference efficiency and generation quality?
UniDisc offers several theoretical and practical advantages over traditional autoregressive AR models, particularly in terms of inference efficiency and generation quality. Firstly, UniDisc achieves higher Frechet inception distance, FID, and clip scores compared to AR models, indicating superior generation quality attributed to classifier-free guidance, CFG, which allows for effective blending of conditional and unconditional predictions during the iterative generation process. Secondly, UniDisc demonstrates significantly improved inference efficiency. It can generate higher quality and diverse outputs within a given compute budget, as it utilizes a discrete diffusion approach that is faster and more controllable than the slow sequential token generation of AR models. Additionally, UniDisc's ability to perform joint image text inpainting without fine-tuning further highlights its versatility and effectiveness, a capability that traditional AR models lack. Lastly, the model's design allows for variable sampling steps tailored to different modalities, enhancing its overall performance in multimodal tasks.
How did you validate the performance of UniDisk? What experimental design and metrics were used to support your claims, particularly in terms of conditional and unconditional generation tasks?
To validate the performance of UniDisk, we conducted experiments comparing it against an autoregressive AR baseline across various tasks, metrics, and datasets. We specifically evaluated both unconditional and conditional generation tasks using a dataset comprising 30 million image text pairs from Datacomp 1B and CC12M. The evaluation metrics included joint perplexity, Frechet inception distance, FID for image quality, and clip score for image text coherence. Our findings indicated that UniDisk significantly outperformed the AR model in conditional generation tasks, particularly benefiting from classifier-free guidance, CFG, which enhanced its performance in blending conditional and unconditional predictions. Additionally, we assessed the model's performance in joint image text inpainting, where UniDisk demonstrated superior capabilities without fine-tuning, further supporting our claims of its effectiveness.
What results did you find that showcase the effectiveness of UniDisk compared to autoregressive models, and what do these results imply about its capabilities in joint image text inpainting?
The results indicate that UniDisk outperforms autoregressive AR models in several key areas, particularly in joint image text inpainting, where it demonstrates capabilities not achievable by prior models. Specifically, UniDisk achieves higher Frechet inception distance, FID, and clip scores compared to AR models, which suggests superior quality and coherence in generated outputs. Additionally, UniDisk exhibits strong joint inpainting abilities without requiring fine-tuning, while AR models struggle to perform similarly, even when explicitly trained for this task. This performance gap is attributed to the iterative generation process of diffusion models, which allows for better blending of conditional and unconditional predictions. Overall, these results imply that UniDisk's unified architecture and discrete diffusion approach significantly enhance its effectiveness in multimodal tasks, particularly in generating and inpainting across both text and image modalities.